Swayam Prabha. Digital India. Educated India.
Hello everyone. These methods, they actually follow one of the principles, CRE, CRT, CRL. Most of the instruments, they follow this one of these methods, but there will be examples that some methods which doesn't follow any of these principles. Okay. First, the pendulum lever principle, which follows the CRT principle, constant rate of traverse. Now, if you see here, in this principle, this is a Lee which is tested here. This is a specimen, and one bottom jaw J2 which moves at constant speed, and J1 also move but not at constant speed. And as J1 moves downward, the pendulum which is fitted on a disc, circular disc, gets deflected. Okay, and the deflection is theta degree, and angle of deflection, and mass is W. So M is mass, and W is the load applied by the pendulum is W. The distance R CG, its CG is at R distance from the pivot. Here it was given, in this case it is at L distance. L is the distance. So pendulum center of gravity and the center of this disc, the distance is L. The rate of extension, so rate of radius of the disc equal to the load mg multiplied by x. X is the horizontal deflection of the pendulum, which is, as per this, it is, if the length is r here, the distance is r, it will be r sin theta. So r sin theta is the M, G, R, capital R, they are all constant. So we can consider that the force applied on the material is proportional to the sin theta, where theta is the angle of deflection of the pendulum. So from this we can calculate two parameters. One is called machine rate of loading, which is denoted by the sign mu, which is that the increase in the load per unit increase in the displacement of the aperture. The displacement of the aperture is r d theta. You know, r is the radius of the disc, and theta is the angle of deflection. If we differentiate the earlier relationship, so we get df by d theta mgr by small r cos theta. So it is by differentiating this relationship, so we can get the df by d theta, and as per the definition of machine rate of loading, so it will be df by r d theta, that means rate increase in load per increase in load is df, and per increase in displacement of the upper jaw r d theta, so which is mu, we get the machine rate of loading mgr by r square cos theta. Okay. So mgr by r square is a constant. So if we make use as a constant, so then for a particular machine, this parameter is known as the standard machine rate of loading, which is denoted by mu 0. It's called standard machine rate of load. So ratio of mu machine rate of loading at say start the theta is 0 degree, and at 45 degree, so we can get the machine rate of loading with the change in the deflection, and it will change as per the cos theta. So the ratio at cos theta cos 0 is 1, and at cos 45 degree it will be 0.707. So another term is time rate of loading. So time rate of loading is the rate at which the load on the specimen increases with respect to time. So it will be, you can see, for inextendable material, for any inextendable material, the jaw 1 and jaw 2, they move at constant speed, the equal speed. So v dt equal to r d theta is the total movement after time dt. So v is the speed of the constant speed of the lower jaw. So d theta dt will be r by r. Then L, the time rate of loading is denoted by the letter L. So L will be Tf dt. So we can just rearrange this equation and we get the time rate of loading mgr cos theta by small r by v by r. Okay, multiplied by v by r. So all other things keeping, except if we remove the v here, all remaining component will represent the machine rate of loading. So time rate of loading and machine rate of loading relationship is L, time rate of loading, equal to machine rate of loading multiplied by speed of the lower jaw. And also here time rate of loading is proportional to cos theta. As cos theta increases, time rate of loading also increases. Okay. So maximum at 0 degree and minimum, that is 0 at 90 degree. The time rate of loading we can calculate. Now try to solve this numerical. In a pendulum lever type tensile tester, the ratio of machine rate of loading at 30 degree Celsius, 30 degree angle and 45 degree angle. Its basic simply it will be the ratio of cos theta. So cos 30 by cos 45, that is 0.87 is to 0.71. So that's the simple relationship Now try to solve this numerical. A tensile tester working in pendulum lever principle has a 16 centimeter disc diameter. So diameter of disc is 16 centimeter. So R will be 8 centimeter radius. So deflection of pendulum. Okay. So at the pivot point for hanging and deflecting the pendulum, the ratio of the force exerted on the yarn in centinewton to the machine rate of loading. So F by mu we want to calculate of the tensile tester at 30-degree deflection of pendulum. Now, if we see the relationship, the force exerted on yarn equal to mgr by r sin theta, where radius of disc is r. In this case, 8 centimeter. And machine rate of loading mu is mgr by r square cos theta. That we have already seen the derivation. So if you calculate the ratio, it will become F by mu will become r tan theta. Okay, r tan theta, r is 8 and theta here angle of deflection is 30 degree. So r tan 30 will be 4.62. Next numerical, similar in nature. Here this diameter is given 10 centimeter, so r will be 5 centimeter, and again the ratio of force exerted on the yarn to the machine rate of loading, F by mu we have seen r tan theta, and r is given 5 centimeter and theta is angle is 20 degree, r tan 20 degree. So we can use the same relationship. So 5 multiplied by tan 20 will be 1.82. Another numerical here. So 20 centimeter diameter here. Here ratio of time rate of loading. Earlier it was machine rate of loading. We want to calculate the time rate of loading at the start point and at the point where pendulum has been deflected by 40. So R is 10 centimeter, so diameter 20 centimeter, R is 10 centimeter. Now try to see here, time rate of loading L. L is proportional to cos theta, as we have seen. Theta is the deflection of pendulum. The ratio of time rate of loading at start and at the point of 40 degree angle of deflection will be, so at the start when the deflection is 0 and this will be 40 degree, L 40, so L 0 degree by L 40 degree, so it will be cos 0 by cos 40 degree, so it will become 1.3. That is the ratio. So time rate of loading increases with the deflection. Next, a tensile tester working on the pendulum lever principle has 16 centimeter diameter. R is 8 centimeter. Okay, of the pivot point of the disc. Okay, the ratio of the time rate of loading at start, again similar numerical at the starting and at the point of deflection of 20 degree. The ratio of time rate of loading in the similar fashion, cos 0 by cos 20, the ratio will be 1.06. So from all this numerical we are trying to understand how the time rate of loading or machine rate of loading is changing, and which will be basically affecting the stress strain behavior of yarn. Now try to solve another numerical. The following data of 20 text yarn tested in pendulum lever principle, where standard machine rate of loading mu 0 is given as 300 centinewton per centimeter. Now the tenacity of the material is given 10 centinewton per text. Breaking extension is given, gauge length is given, traverse rate, that means traverse rate of the bottom jaw, which is moving at constant rate, and time to break we have to calculate. So rate of breaking extension is also given. So yarn linear density is 20 text, which is given. So maximum force applied on the specimen is breaking tenacity is 10 centinewton per text breaking strength. So maximum force encountered by the material will be 200 centinewton. It is 200 centinewton F max. So standard machine rate of loading is given 300 centinewton per centimeter. So reciprocal of mu 0 indicates the movement of upper jaw per unit increase in the load. That means centimeter per centinewton. So which is denoted by, so it's 1 by mu 0. So it's a 1 by 300 centimeter per centinewton. Okay, 1 by 300. So total movement of the upper jaw is F max by 300 will be 200 by F max is 200 centinewton we have calculated earlier, and 1 by 300. So it will become 200 by 300. Now velocity of the lower jaw is given, which is constant, 50 millimeter per minute. From there, so another data is given, the elongation. So breaking extension is 10% and gauge length was given 20. So breaking extension is 2 centimeter. That means total extension before break. So we can calculate the total movement of the lower jaw before breakage will be total movement of the upper jaw plus breaking extension. as the upper jaw moves. So that movement if we can calculate. So what we have calculated, this is the total movement of the upper jaw 200 by 300 and breaking extension of the yarn 2 centimeter. So if we add, it will become 2.66 centimeter. That is total movement of the lower jaw. And constant rate of traverse of the lower jaw, it was given 5 centimeter per minute. Okay, and it has moved for 2.66 centimeter. We can calculate the time required. Time required is 2.66 by 5. It will be 0.533 minute, and time required for breakage will be 32 seconds. So in this way we can get the total time required to break a material in pendulum lever principle, where it works in constant rate of traverse principle. So similar numerical, we'll see here, just data changes. So traverse rate is given, gauge length is 20 centimeter, breaking extension is 20%, and tenacity is 12 centinewton per tex, 20 tex yarn, and the standard machine rate of loading is 400 centinewton per centimeter. So same way we can calculate the total, the maximum force encountered, that is breaking load, will be 240 centinewton, 12 multiplied by 20 tex. Standard machine rate of loading is given. So if we take the reciprocal of that, it will be 1 by 40 centimeter per centinewton, and total movement of the upper jaw will be F max by 400. So this is the total movement of the upper jaw. Velocity of lower jaw is given 5 centimeter per minute, and breaking extension 20% of the gauge length of 20 centimeter. So breaking extension is 4 centimeter. So we can calculate the total movement of the lower jaw, which will be the movement of upper jaw plus extension of material. So this way we can calculate, it will become 4.6 centimeter. So 4.6 centimeter is the total movement of lower jaw, and constant traverse rate is 5 centimeter per second, which is given. So we can calculate the time required, which is 0.92 minute to break the yarn. Okay. So total movement of the lower jaw divided by velocity of the lower jaw. So 4.6 by 5. So we can calculate, this is the minute. From there we can calculate the, it will, in the second it will be 0.92 minute means, so 0.9 to 55.2 seconds. Next method is the Stelometer. So Stelometer works on, again, the pendulum lever principle. Here the blue color, it's a pendulum, and the beam is there. So the pendulum is fitted on the beam, and center of gravity of the pendulum is at this point. The loading of the specimen is carried out by a pendulum system which is mounted in such a way that it rotates about its center of gravity. Okay. Now, here you have two jaws, jaw 1 and jaw 2, and the specimen is fitted on this, fixed on these jaws, and the beam is a heavy beam relatively, and when the beam is released, the beam will rotate clockwise so that its center of gravity comes just below this pivot point, and this there will be deflection, and that deflection and the weight of the pendulum which will be responsible for applying load on the specimen. So if we see the diagram, this is the initial point, left side, material is fitted, and when we release the beam will get deflected, and due to the presence of material sample specimen, the pendulum also will get deflected. This is the beam and here is the pendulum. So due to the deflection of the pendulum, the load will be imparted on the material, and that these jaws are same as the Pressley jaw that we have already discussed earlier. And this, with the diagram we can see here, F is the force applied on the material, and the center of gravity, the weight of pendulum is W, and the distance from pivot point O to this center of that the center of gravity of the pendulum depends on the deflection, that this is fixed, okay, and the load applied on the specimen depends on the deflection, angle of deflection. So let us see. So if we try to balance the moment, clockwise and anti-clockwise moment, so clockwise moment is F multiplied by OQ. What is OQ? OQ is the distance from the pivot point to the specimen, okay, this is OQ, and W is the weight of the pendulum, and OG sin theta, that is horizontal deflection of the center of gravity of the pendulum. So this is the OG sin theta. OG is the distance from the pendulum center of gravity G to the pivot point, which is fixed. So using this relationship, we can calculate F equal to W multiplied by OG by OQ, where OQ and OG are constant, and for a certain instrument W can be constant. So what we get, F is proportional to sin theta. So here we will see, as the pendulum deflection increases, the load on the material increases with the sin theta. So F is proportional to sin theta. Okay. Now the deflection of the pendulum and the designing of this beam is kept in such a fashion, when we release this beam, this deflection will be following at the rate that it will increase at where sin theta is kept constant. So this is not the simple design. So if the sin theta increases at constant rate, so increase of sin theta will be constant. So that's why we can maintain this instrument as constant rate of loading. This works in constant rate of loading principle, because due to the design of the instrument, as the theta increases in such a fashion, sin theta increase will be at the constant rate. So this is explained here, and there are pointers, two pointers are there, pointer P1 and P2. They measure the elongation and load. Okay. Now try to solve this numerical. In a stelometer, the breaking load of a cotton fiber bundle, is found to be 14 Newton and 10.5 Newton at 0 gauge length and 3 millimeter gauge length respectively. The corresponding mass of the tested fiber bundles were found to be 2 milligram and 2.1 milligram respectively. Okay. So we have discussed earlier these jaws, these are two jaws, and these are the fibers. Total jaw length, the total width of the two jaws together when they are touching, it is typically 11.8 millimeter. And when we take out this jaw, open this jaw and take out the material and take the mass, for first case, in this case, the mass was 2 milligram, and at 3 millimeter gauge length, when there is a gap of 3 millimeter between these two jaws, there is 3 millimeter gap, and when we take this material, this is test 1 and test 2, and here the length will be 11.8 plus 3, so 14.8 millimeter. So in that case, we take the mass 2.1 milligram. So here it's not sure that we are taking the same number of fibers, maybe number of fibers are different, but we are getting the 3 millimeter gauge length, they are getting 2.1 milligram mass, and the strength becomes 10.5 Newton. Okay. Now let us try to solve using the relationship that we know, the relationship So gram per text if we want to calculate. So breaking load in kilogram force, bundle length in millimeter, and mass of the fiber bundle milligram. So at 0 gauge length, the bundle length is 11.8 millimeter and breaking load is given 1.4 kg force. So we can calculate the bundle tenacity using this relationship, 8.26 gram per text. And for 3 millimeter gauge length, this will become 7.405 gram per text. So here also you can see the weak link effect as the gauge length increases from 0 gauge length to 3 millimeter gauge length, the tenacity of the bundle also reduces. Now try to see another numerical. When a cotton is bleached, the angle of deflection of pendulum at stelometer is decreased from 30° to 20° in a stelometer. The percentage change in breaking load after bleaching. So it's simple. We know that it follows the relationship with the sin theta. It's proportional to the sin theta. So we will just get the ratio of sin 30 and sin 20. So sin 30 is 0.5 multiplied by some constant, and at 20° it will be 0.342 multiplied by k, and we take the ratio and or percentage change. So F30 minus F20 by F30, and we get that 30% drop. So percentage drop is 30%, 31%, 31.6%. Percentage drop in strength after bleaching will be 31.6% when we test the bundle strength by Stelometer. So while measuring the tensile properties of cotton using Stelometer at 3 millimeter gauge length, a cotton fiber bundle of 10 milligram weight registered a breaking load of 60 Newton. So bundle tenacity using the same relationship. So 3 millimeter gauge length means the length of the specimen will be 14.8 approximately. And breaking load in kg, so Newton is given, so we have to calculate convert it to kg. So we get, after conversion, we get the tenacity in gram per text 8.88. This simply the matter of conversion, one can always do the conversion. Now similar numerical. So at 0 gauge length in the Stelometer, the bundle weight is 15 milligram and breaking load is 80 Newton. So bundle tenacity will be, so tensile strength or tenacity of fiber bundle, the same numerical we get 0 gauge length, it will become 11.8. So approximately 6.29 gram per text. Now another numerical similar, moisture of cotton increases, so moisture content increases, the angle of deflection, so as moisture content increases, the cotton becomes stronger, so angle of deflection in stelometer increases from 30 degree to 45 degree while breaking. So increase in breaking strength, same process. So force equal to constant into sin theta. At 30 degree it will be 0.5 K and 45 degree 0.707 K. So the ratio will be, the percentage change will be 41.4%. Percentage change in breaking strength. Next principle is that beam balance principle. So beam balance principle, we know this is the beam. So the load, so this is the unknown load P, and here F, we apply the force F in the other side, and C is the fulcrum point, and the P can be calculated based on the ratio of the distance AC and BC. So if this ratio changes, then the P value will change when F is kept constant. So that's the principle, and the ratio is, the relationship is force P multiplied by the distance from the fulcrum point and the F multiplied by distance from the fulcrum point AC. So this is the relationship where P is the force P of the specimen. This force on the specimen can be varied by, so P equal to F multiplied by AC by BC. So this P can be changed by changing the force or by changing this parameter, length parameter, that is distance, or by changing the distance from the fulcrum point. At center point, if at center point, F will be equal to P. Now with this principle, the instrument which works, it's called the Pressley fiber strength tester. So in Pressley fiber strength tester, we use the fiber clamp, the same fiber clamp which we use in the stelometer. These two clamps are, standard clamps are interchangeable. That means here at 0 gauge length, again we will consider the fiber bundles length will be 11.8 millimeter. So this instrument is also used for fiber bundle strength measurement. So here AB is the beam. AB is beam and O is the pivot point. Okay. And here the sliding weight is there. Sliding weight, and OB is fixed for this instrument. So OB is fixed, but due to the sliding, this is the weight of the mass is there here, and as the sliding weight slides downwards, the distance from the fulcrum point increases. Okay, and that, as the distance increases, that will increase the load on the specimen. So A dash O is the distance at any distance from the fulcrum point of the loading sliding weight at any instant. So as this sliding weight slides down, so A dash O increases and it goes on increasing until the breaking point reaches, and the design of the instrument is such that as soon as it breaks, the material breaks, immediately the sliding weight will stop. So it will not go further. That's the design. And using the simple relationship of beam balancing, we can calculate the load on the specimen, breaking load on the specimen, if we know the distance at which the slider slides. Okay. Initially there will be certain slight inclination so that the sliding weight slides down. So the rolling weight is W, and as the distance A dash O increases, the load on the instrument, load on the specimen increases, and as this distance OB is constant, weight of the slider W is constant. So this distance slided, the sliding distance, that is O A dash, this distance is proportional to the force applied on the fiber bundle. So this, from the relationship, that's how we can gauge this sliding distance in terms of force. If we have this constant values, okay. So length here is 11.8 millimeter at 0 gauge length, and from here we can calculate the Pressley index. Pressley index is given by breaking load in pound and bundle weight in milligram. And we can get this relationship, the tensile strength in gram per tex equal to 5.36 multiplied by Pressley index. This is for 0 gauge length. Okay. So bundle tenacity in this instrument is given by, if we, this constant 0.1 comes from the unit conversion only. So breaking load in Newton, bundle length in millimeter, and mass of the fiber bundle in milligram. That is the relationship. It's centinewton per tex, and here it's given, it's in pound. Okay, so we are converting it to Newton and pound. Relationship is 0.1 Newton equal to 0.2248 pound. Now you can see here, this is the relationship we can get, and 0.1 breaking load in pound divided by 0.2248, bundle length is given 11.8, we know bundle strength. So, and mass of the fiber bundle in milligram. So from this constant we can get the value 5.25, and this remaining part, breaking load in pound divided the mass in the fiber bundle in milligram, is Pressley index. So point that we have seen. So here we will calculate centinewton per text. So it is becoming 5.25. But if we take in gram per text, it will be 5.36. That's the relationship for 0 gauge length. Let us see what happens to the 3 millimeter gauge length. 3 millimeter gauge length, only this parameter will change. 11.81 become 14.81. So for gram per text, it will become 5.36. For 3 millimeter gauge length, it is 14.81. No other changes. So here the relationship is 6.58. So bundle tenacity in centinewton per text equal to 6.58 multiplied by Pressley index. So load of the specimen P is proportional to the distance traveled by the sliding weight. So the rate of loading is governed by the speed of rolling. So here we'll see that the speed we cannot keep constant because it's a sliding. Okay, so speed is not constant. So rate of increase of A dash O is not constant. So we cannot keep this instrument, we cannot call this instrument as CRL principle. It's not the CRL principle. Constant rate of loading principle is not following. But whereas in case of this Stelometer, the deflection rate we can control. So this instrument, that's why it doesn't follow CRE not the CRL. So CRE definitely is not there because the sliding rate is changing. So extension we cannot control, and CRL it's not working. But if we can control the velocity of rolling by certain means specially designed, then we can control the achieve the CRL test, but which is very difficult. Now try to do a numerical. In a Pressley fiber strength tester, the breaking load of a cotton fiber bundle at 0 gauge length is 12.5 Newton. At 0 gauge length, it's 12.5 Newton. The mass of the fiber bundle is 2 milligram. What will be the Pressley index and bundle tenacity? So it's very simple. So breaking load is given, and we can convert it to pound. So 12.5 Newton equal to 2.81 pound. So in Pressley index, pound is required. Mass of fiber bundle is 2 milligram. So we can get directly the Pressley index 1.405, and bundle tenacity in centinewton per text The relationship we know, 5.25 multiplied by Pressley index, it is 7.37. Similar numerical where the at 3 millimeter gauge length in Pressley index, Pressley tester, the breaking load is 2.1 pound and the mass of the bundle is 2.25 milligram. So Pressley index we can calculate. Breaking load is given, mass of the fiber bundle is given 2.25 and Pressley index is breaking load in pound by mass bundle weight in milligram. So 2.1 by 2.25, it will become 0.91, and what we have to calculate, the bundle tenacity in gram per text. So it will become at 3 millimeter gauge length. So the relationship is 6.72 by 0.93. It is 6.25. Okay. Loading by spring, and this is the instrument which works both in CRL and CRE principle, and which is called Cambridge extensometer. Here in this instrument, the loading is done by the spring, and two motors are there, M1 and M2. They rotate at constant speed, but not in continuous fashion always. With this attachment, when we need constant rate of loading, the motor M1 rotates at constant speed and the upper jaw is connected with the spring, and lower jaw J2 is connected with another follower which is connected with a rod, screw rod driven by the motor. When motor M1 rotates at constant speed, that follower F1 will move upward at constant speed, which will result the extension of the spring, okay, helical spring at constant rate, so that we know that the spring is actually the load increases with the same proportion as the extension increases. So as the extension is increasing at constant rate, that means the spring is stretching at constant rate, so loading is increasing at constant rate. So specimen fiber or yarn specimen is stressed or loaded at constant rate. Okay. So if we want to work at constant rate of loading, then motor M1 rotates at constant speed. At that point, the motor M2 initially was stationary. It was not running, it was stopped. But due to the extension of the material, so extension characteristics, the leaf spring will touch the connector C2, and connector C2 is connected with the motor M2, As soon as the leaf spring touches with the connector C2, due to the extension of material, the motor M2 will start rotating, and as motor M2 starts rotating, the follower F2 will take the lower jaw downward, and when the lower jaw is moving downward, so there will be disconnection, again the motor M2 will stop. So in this way the process will continue. That means the motor M1 will move continuously and applying the load at constant rate, but due to the extension, the motor M2 will rotate intermittently. So motor M1, that is rotational motion, whatever the movement of follower F1, which that represents the extension of the material, and F1 upward movement of the follower F1 represents the load on the material, and downward movement of the follower represents the follower F2 represents the loading on the material, and these are explained here in detail. So I am not going to discuss all these things in details because this is explained here. So in CRL condition, as has been explained, so M1, motor M1 will rotate continuously, and to test in CRE principle, the reverse way, motor M2 will initially be stopped, it will be stationary, and motor M2, so M1 will be stopped and motor M2 will rotate continuously. So then we will get similar fashion, we will get the system working in CRE principle. So the thing is that the motor M1 is responsible for loading and motor M2 is responsible for elongation. And next process is inclined plane principle. Here one heavy carriage is there, and which is connected with the fixed jaw through the specimen, and as the other side, so K is the fulcrum point, so J1 is the one end where the material is attached, and other jaw is J2, which is connected with the moving carriage, and other side of the beam, that's platform, is placed on the moving platform, which moves continuously in the downward side. As the platform, this platform moves downward at constant speed, so the point A, other side of the beam, will be lowered down at constant speed. So which will be actually this, as it is moving down, so sliding will be there and the carriage will move downward and material will be loaded. So let us try to see the animation. Initially it is horizontal. Now the other end B, it's moving downward. So initial position of the point B was A. So it's moving down at constant speed. So the angle theta, angle of deflection, is increasing gradually, and W is the weight of the carriage. Okay, and from here we can get from the triangle which is formed ABK, we can get sin theta, the angle theta is the deflection of the beam. So sin theta will be AB by KB. So AB by KB. So KB is constant. So for this instrument, KB is constant. Now if we change this AB distance, that means AB distance at constant fashion. If we increase the AB at constant speed, that means by lowering the point B at constant rate, we will be able to achieve the constant rate of loading. So P dash is W sin theta. Okay. Let us see once again. So it is moving downward at constant speed. So constant speed, we can lowering down at constant speed. Here rack and pinion arrangement is there. We can use any other arrangements. Okay, so that way we are lowering down, and this B point, it's not fixed on the platform. Blue color, it's placed on the platform. Now the load applied on the specimen is W sin theta. Okay, as sin theta increases at constant rate, because AB is increasing at constant rate, so we can maintain the constant rate of loading. So this is explained here. So constant rate, load is increasing, sin theta will also increase at constant rate. So load is increasing at constant. So it works on CRL principle. Now let us try to solve few numericals. In an inclined plane type tensile testing machine, which we have just discussed, the distance from the pivot point to the dropping end is 23 centimeters. That's fixed, okay, for the machine. The weight of the carriage is 140 Newton, and the rate of lowering down the dropping end is 2 millimeter per second. What will be the rate of loading on the specimen? So we know the relationship P equal to W sin theta, where W is the mass of the carriage and theta is the angle of deflection, and which is equal to W x by AB. Okay, AB is known, is constant, and x is the amount of lowering. Okay, AB distance, which is given here at 23 centimeter or 230 millimeter, and weight is 140 Newton. So rate of lowering is x, that is 2 millimeter per second. So rate of lowering is given, and from there we can calculate the rate of loading. 140, 2 is the rate of lowering, the rate of, that means rate of increase in of x value by 230. 230 is the distance from the pivot point to the dropping end. So it becomes 1.21 Newton per second. Next numerical is that in an inclined plane type tensile test machine, the distance from the pivot point to the dropping end 24 centimeter, the weight of the carriage is 90 Newton. Now to have the loading rate 2 Newton per second. So we want to fix the rate of loading. Now we want to calculate the rate of lowering down. So at which rate we have to lower down the other end. The same relationship we have to use. Here distance is given 240 millimeter and weight is 90 Newton, and rate of lowering x, it's P is given, rate of loading is given 2 Newton per second, P is given, so x we have to calculate. So rate of dropping is x. So from there we can calculate the rate of dropping. Weight of carriage is known, so it will be 5.33 millimeter per second, using the same relationship. So if we lower down the other end at the speed of 5.33 millimeter per second, then we will be able to achieve the rate of loading. So rate of loading we can fix, we can change the rate of loading. So what we have to do, we have to calculate the rate of lowering of the dropping end, which is x, to have a rate of loading of 1.5 Newton per second. So we have to calculate x in this relationship. So P is given 115 Newton, sorry, P is given 1.5, P is given 1.5 Newton per second, W is 115 Newton, okay, and here AB is 20. From this we can calculate the value of x. So it's given here. So P is 1.5 Newton per second and x we will get, that is 2.6 millimeter per second. So if we drop the dropping end at 2.60 millimeter per second, you will be able to achieve the rate of loading 1.5 Newton per second. So we will stop here, and next class we will discuss the ballistic or impact principle of loading. Till then, thank you.